Now we're going to learn a little something about events. So in the previous units, we have talked about concurrency, which is the idea that you want to run multiple things at once. And we talked about threads, which is how that concurrency is achieved in many programs. So threads are not the only way to write and run a highly concurrent program. So today we're going to look at the alternative, which is called event-based programming, and we'll learn what events are and when they're a good idea. So if you look at the iPad, like we see that like when we have threads, what's really happening is that we have two threads, and they're running along, executing different instructions, and really the control of when a particular thread stops and then another thread runs is done by the OS, right? So if you remember, there is this idea of a context switch, and the OS can basically say to any process at any point of time, I'm going to stop you, and then I'm going to put you to sleep, I'm going to save your state, and then I'm going to run a different process. And the same is true for threads also. So in thread-based programming, we use threads to do multiple units of work at the same time, but we don't really have control over scheduling. Right, so the OS is in charge of like scheduling a particular thread or a particular process. So what makes thread-based programming difficult is that, especially if the threads are accessing the same variable at the same time. For example, in the demo that we saw earlier, we saw two threads which were accessing the counter variable at the same time. And because of that, because the threads were interleaved, what we saw was that even though the counter should have been incremented first by one thread and then by the other thread, they often did it at the same time, resulting in incorrect behavior. So broadly, this is an entire class is called like concurrency problems. It happens when you're using threads to access the same data and you're trying to have correct behavior in the program. So the more shared state that you have, the same variables that threads are accessing, the more threads you have, the harder it is to actually get correct behavior. This is what makes concurrent programming really hard. So so because of this, in situations like, let's say you're writing a web server, right? And a web server is a piece of software where, let's say you go to google.com, and when you type in google.com, you get a page. And the web server is the software that is responsible for taking the address or getting your request for google.com and then responding back with a page. So it serves you web pages. So that's a web server. Now, as you can imagine, there must be like millions, potentially like hundreds of millions, or maybe even billions of people going to google.com at any given point of time. So we need to be able to sort of like serve all those requests pretty quickly. And so a web server is a sort of like it's a piece of software where efficiency is very important, and you want concurrency. So if you're running your web server on a machine with like lots of cores, then that you want to be able to use all those cores. So before we sort of like head into events, let me actually sort of like quickly give you a recap of the different hardware pieces that we're going to be talking about here, right? So you have on modern processors, you have let's say this is the whole computer, right? And then you have multiple cores. So this is core 1, this is core 2, and so on, right? So and inside this core, you may have different processors, right? So the way to think about this is that a processor, or let's say a hardware thread, is capable of running a thread at one point of time, right? So basically in this setup, you have a 2-core processor, and then each core has 2 hardware threads. So we have 4 hardware threads total. What this means is simultaneously you can run 4 threads at the same time, or 4 processes at the same time, right? So in this particular machine, when let's say you're running a web server on this particular machine, you want to use all 4 hardware threads at the same time. You want to keep all your cores utilized, right? Now, one other thing that makes all of this sort of like more interesting is that the way your computer is architected. So you will have a core. Let's say we have 2 cores here, and there is a set of like fast hardware caches that are associated with your core, like L1, L2, L3, and so on. Right. So actually, like not L3. So L1 and L2, and these are private to each core. So each core will have its own L1 and L2 caches. These are really fast caches. So for example, if you are accessing a variable X and if it's in cache, that's a variable that's really fast to access, like a few cycles. You will also have what is called a shared last level cache. Right, and below that you will have memory. So the reason all this stuff is important is because when your threads are actually running, like let's say there are 2 hardware contexts here, and then there are 2 processes running, they share all of this stuff. So these 2 hardware threads or contexts or which are running have access to this L1 and L2. They share L1 and L2, whereas these 2 share this L1 and L2, but they all share this L3 cache, right? And below that you have memory. So when you're running or you're building a highly concurrent program, it becomes really important to know all these details, because like for example, if you're trying to access something that is in your L1 or L2 cache, that is really fast. Whereas if you're trying to access something that's in your last level cache or in another core's L1 cache, which means it needs to be brought down and then brought up, that is going to be much more expensive. So these are all details to keep in mind. The sort of like the programming that we're going to do in this class will not really depend upon knowing these details, but it is something to know in the context of like concurrent programming. Okay. All right. So getting back to our sort of like initial thing. So in the previous example, this kind of like processor we had, when you have web server, you want to keep all of them utilized at the same time, right? So now a different way to do concurrency is to do this, right? So what happens is that on a single processor, you have what's called an event loop. Right. So this is just an infinite for loop which is keeps spinning, and what it is doing is waiting for events, right? So what happens is there is an event that arrives, let's say, and what the event loop will do is it will process that particular event. So it will do a small amount of processing to handle that event. Right, and then it'll keep back. Then it'll go back to its infinite loop, and it'll keep doing that. So every sort of like event that comes along, the event loop is going to do a small amount of processing, and it's going to go back and it's going to keep waiting for events. Now, what happens if there is a large amount of processing that we need to do, and for example, we need to talk to somebody else, and there's some amount of work that needs to be done, so it can't be done immediately. So in that case, like what you do is you do the first part of the work. So let's say you have the event loop, and then you got this event. So you do the first part of the work, right? And then you basically you send it off. So when this first part of the work finishes, it will return as another event to your event loop. Instead of like a fresh request, it will be like, oh, here's a request that like we've done some work on. And the event loop will once again look at this, and it will be like, I see that we've already done some work, and now I'm going to do the second part of it. Right? So what is really happening here is that this event loop runs forever, and there's no operating system scheduling involved. This whole thing is a uniprocessor. It's a single processor that is running, and then there's no need for multiple threads or anything like that. It's very simple programming. So you have one event loop which keeps running. Whenever it gets an event, it takes time off. It processes that event for a really small amount of time, and then if a lot of work is done, it does a little part of it and then puts it back in the queue as another event. And then it keeps looping. So the nice advantage of this architecture is that you never have to worry about two threads writing to the same location, right? For example, if you did the counter increment program that we did earlier, you would never run into a problem where there are two threads which are trying to write to the same counter, and therefore you have incorrect behavior. In an event-based architecture, you will always get correct behavior, right? So I'm not going to go into too much details about event-driven programming, but it is something useful for you to know about. And the key insight, right, that you have to remember is in threads, we are allowing the operating system to do the scheduling for us. So we're basically saying, I'm going to run threads, and the operating system is free to stop the threads at whichever point it deems is good, and it will restart the threads, and I'm fine with that, right? So that's one model, and it works for many different applications. With event-driven programming, what we're basically saying is we're not going to let the OS do any of that for us. There's only going to be a single thing going on at any point of time. This is the event loop and the stuff that it does. So there's no need for the OS to be involved in scheduling anything. There is one process that's running, and there's one processor. So there's like absolutely no scheduling required, just that one process runs forever. But instead, what we do is we do what the OS was previously doing ourselves. So whenever we get an event, we stop this infinite loop, and then we go and we do a bunch of work, and then we put it back into our event queue, and we say we're going to do that at a later point of time. So if you think about it, what we are doing is we are doing user space scheduling among events, right? So we're just like controlling what we want to do a little bit better. And this is a trade-off that we will see again and again in many parts of like operating systems, right? So when you want something to be more general, you allow the operating system to do it, but there will always be cases where the operating system will not do the best job because it doesn't have all the information. So in that case, what we do is we allow the applications themselves to run the show, to basically, because they know everything that's going on, they can do the scheduling themselves. And event-driven programming is sort of like an example of this, where we're saying to the operating system, like, please don't schedule anything, we're going to handle everything. And of course, the cost of doing something like this is complexity, right? So now instead of like the operating system like scheduling things for us, we're now going to have to explicitly schedule stuff. We're going to be saying, I've done like the first part of this work, and now at a later point of time, I'm going to do the second part of this work. So we're going to have to remember what we did previously, and then we're going to have to continue. So all of the nice abstractions that the OS was providing goes away. But in return, we get typically higher performance. And we also get freedom from data races and concurrency bugs. So it's kind of like a sort of like an interesting trade-off. And actually, in the research community, back in the day, there were like lots of like back and forth between like eminent researchers who basically said, one side said like, all programming should be done with threads. And then the other side said, that's not a great idea, let's use events, like everything should be done with events. And then they went back and forth. And of course, like there's no one solution that works for everything. You have to really look at the situation to decide. But it's one example of how there was this like nice back and forth, which brought forth many technical details to the community. So one other sort of like snippet of information I'm going to leave you with is, you might have heard of the Nginx web browser. Nginx is written using an event-driven architecture. So in the initial web servers were all written using thread-driven architecture, where the absolute naive thing to do is every time the web server gets a request, it spawns a new thread to handle that request. Now, of course, like, spawning a new thread is not cheap. And in some of the other videos, we'll talk about that. But spawning a thread is not cheap, so this architecture did not really give like great performance. So the next thing they shifted to was the idea of like a pool of threads. So they wouldn't spawn a new thread. Instead, they would spawn like 20 threads, and then it would keep them running all the time. And whenever a request comes in, they would then say like, oh, thread 1, here's your work, go do it. So it was like a thread pool architecture. And Nginx, for example, uses an event-driven architecture, and Nginx has quite high performance. So one resource I want to leave you with, and this will be part of the course materials also, is that there's a website called the Book of Open Source Architectures. So this is a website where basically like people write about like Nginx and Apache Web Server and all of these other great open source tools, and they talk about like how these things are architected. So if you want to get a good sense of like how complex these systems are designed, I highly encourage you check this out.